Greetings. This is Electronic Circuits 1, lecture number 3, and I am Razavi. Today we will talk a little more about carrier transport, meaning how we move charge in a semiconductor. And then we are ready to build our first semiconductor device, namely the PN junction. Before we do that though, let's quickly review what we learned in the last lecture. So let me pull this over here. What we saw last time was that since the number of free electrons in pure silicon is relatively low, about 10 to the 10 per cubic centimeter, pure silicon is not a very good conductor. So to increase its conductivity, we can introduce impurity atoms into it. For example, phosphorus as an atom that has one extra electron that can be donated, or boron that has one fewer electron and can create a hole. So we said that in N-type semiconductors, we dope them with some sort of donor, for example, phosphorus. And because phosphorus has 5 electrons in its outermost shell, it ends up with one free electron that is capable of carrying a current. And if the doping level is high enough, let's say 10 to the 15 or 16, then the number of free electrons per cubic centimeter is approximately equal to the number of dopant atoms that have been introduced into silicon. And that means that number of holes has fallen to Ni squared over Nd. Okay, we can also create a large number of holes in a semiconductor by introducing acceptor atoms, such as boron. Boron has only 3 electrons in its outermost shell, so it creates a hole. And that hole, we have as many holes as boron atoms. So again, if the density of boron is high enough, we have a hole density approximately equal to the number of acceptor atoms introduced into silicon, and then the number of electrons has fallen considerably to Ni squared over Na. So these two types of doping help us create majority carriers in the form of electrons or majority carriers in the form of holes. And as we will see in a few minutes, this is the basis for building a PN junction. Now, we also started looking at carrier transport, meaning how charge moves in semiconductors. And we considered a piece of silicon with some amount of doping in it, N-type or P-type, and with a width of W and a thickness of H. And we saw that we have 2 mechanisms, one of which is called drift. Drift simply means we apply voltage across the semiconductor, and that creates a current because we have created an electric field inside the semiconductor. For semiconductors, the velocity of carriers, similar to a parachuter, reaches a terminal velocity and is equal to mu times the electric field, mu being the mobility of the carriers, electrons or holes. So we derived an equation for the total current that flows, which was given by the velocity of the carriers, times WH, which is the cross-section area of the object we're going through, times the density of electrons or holes, times the charge on one electron to give us the total current. And we saw that in semiconductor physics, we generally would like to express the currents as current densities. That means the amount of current that passes through one unit area of the object. So 1 square centimeter, for example. And that would be J, and is given for both electron flow and hole flow by this expression. So here we are assuming that there are some free electrons that carry current, and there are also some holes that can carry current. Now, one might be much less than the other, but in the general case, we need both of these terms multiplied by the electric field. All right. Now, I think I forgot one term here. We need to add a Q term here. So let me make sure that I don't forget that. We need to multiply this by the charge of one electron so that the overall expression is in amperes per square centimeter. Okay, so this is one mechanism for current conduction in a semiconductor. There's an electric field, there's a velocity, there's current. But there's another mechanism that does not even require a voltage or an electric field, and that is called diffusion. So today we will talk about diffusion. All right, so today's lecture will start by talking about diffusion and how we quantify that effect. And then that completes our study of current transport. And then we go to the first electronic device that we can build, the simplest, namely the PN junction. So we will study some applications of the PN junction to give us some motivation for why we study this device. Then we'll talk about the basic structure of this device and try to familiarize ourselves. We'll take our time and slowly understand what's going on. And then we consider it under one condition, which we call equilibrium. This device can be considered in different conditions, namely 3 conditions. So we will study only the first one today, and then the next few in the next lecture. Okay, so let's talk about diffusion and see what that means. All right, so as I said, we could have current without voltage. Strange but true. We could have current without voltage. Now, that goes against everything that we have thought about before, Ohm's law and everything else, but just hang on there, and we'll hang in there, and we'll see how that happens. So I would like to show you a quick example of what happens in the process of diffusion. So here we have a glass of water, and I'm going to drop some ink into here. So what happens? Well, as you can see, the ink molecules are diffusing. The ink molecules are going everywhere. Not just downward because of gravity, but also sideways. They are going in every direction. Why is that? Why do the ink molecules prefer to redistribute themselves? Well, this is because the ink molecules have a high concentration where they were injected into the glass, right here, and they would like to equalize their distribution, equalize their concentration. So what they do is they go from the high concentration area to the low concentration areas, and that is called diffusion. So diffusion is defined as movement of charge carriers. Now, of course, it doesn't have to be charge carriers. It can also be ink molecules or anything else you would like. But in our case, we are interested in charge carriers. Movement of charge carriers from a region of high concentration to a region of low concentration. Okay, just the way the ink molecules decided to redistribute themselves. So what we see is that if we inject charge, if we inject, for example, electrons into a piece of semiconductor, then at the point of injection we have a high concentration. And they don't want to stay there. They begin to diffuse away into the regions that have a lower concentration. And that's how we get a current, because the charge is moving from the high concentration region to the low concentration region. And that is current, because current is defined as the movement of charge. So, all right, so that means that if I take a piece of semiconductor, so let's say N-type or P-type, doesn't matter. So let's say N-type semiconductor, and somehow I inject electrons into here. So injection of electrons. So if I inject electrons here, right around here we have a high concentration. So if we plot as a function of distance, starting from here, at this point we have a high concentration of electrons because we're injecting lots of electrons. But electrons don't want to stay here. They diffuse away. So if we go over here and measure the concentration of electrons, it will be lower. If we go here, it will be lower, and so on. So it goes down. We don't know exactly in what form it goes down, but it goes down. So we have a high concentration here and low concentration here. We say we have a gradient from here to here, gradient of concentration. And we think of these electrons as rolling down this gradient. This is like a slope on a hill. So they would like to roll down this gradient and go to the other areas where the concentration is lower. So we have an electron here, and the electron rolls down this hill because we have a high concentration here and low concentration here. And a similar effect can occur with holes. Just keep in mind that if electrons are going from left to right, the conventional current, which is positive, is going from right to left. For holes, that's fine. If holes go from left to right, then the conventional current also goes from left to right. So these two must be distinguished. Very well. So how can we quantify a current resulting from diffusion? We don't have an electric field, we just have different concentration levels. Well, what we are thinking is that the amount of current, now we can write I or we can write J, we'll write J. We are thinking that J, the current that flows through the semiconductor at any point, if I stand there, should be proportional to the slope of this concentration. You can imagine that if the concentration is constant from here to here, let's say there's no injection, there is no diffusion, right? If you can see that now the ink has completely diffused and there's no more tendency to diffuse anymore. So if the concentration is constant, if the gradient or the slope is 0, then there is no more diffusion. So it must be proportional to the slope of this concentration. So what I'm thinking is that this should be proportional to the slope of the concentration, N for electrons, P for holes, with respect to distance. That's what we intuitively expect. Okay, all right, so then how do we write this as an equation? Well, we say it has to be equal to dN over dx, and then some proportionality factor, again to get the units right, and we call this d sub n. D sub n is called the diffusivity of electrons. So this is called d diffusivity of electrons if it's d sub n. This equation is not complete yet. Why? Because the current has to be in amperes per square centimeter. But it's not amperes yet because we don't have any notion of amount of charge that we have, charge in coulombs. So we put a Q, we add a Q, meaning charge per electron. At the end, we multiply it by Q so that this whole thing is now in amount of coulombs that pass in 1 square centimeter in 1 second, and that would be J. All right, so that is the diffusion current arising from electrons, from the different concentration of electrons, if the concentration is not constant. Now, as an exercise, you need to prove that even though these are electrons, the current, the conventional current, would still be like this, and in other words, we don't need a negative sign. We do not need a negative sign here, even though these are electrons. So just think about it for a few seconds, and you will see why this sign is positive, not negative. All right. What if we have both electrons and holes available in a piece of semiconductor, and both of them have concentration gradients? Well, a similar effect will occur. So we will have dP over dx if there is a concentration gradient for holes, and then we will have to multiply it by some diffusivity. The diffusivity of electrons is not the same as diffusivity of holes, so we will call that d sub p, and then we just add them up. So in general, if we have both electron concentration gradients and the hole concentration gradients, the total current density is given by, starting from electrons, we write dn, derivative of n with respect to x, minus dp, derivative of holes with respect to x, and then the whole thing multiplied by electron charge. So again, you need to prove to yourself that in this case, this sign is positive and this sign is negative when we consider the gradient in hole concentration and the gradient in electron concentration. All right, so that's a nice little equation that we have for diffusion. We don't need electric field, we just have different concentrations at different points in a semiconductor. Okay, so let's look at a quick example to see how diffusion actually occurs and what consequences we should expect. So I perform an experiment. I take a piece of semiconductor. So let's draw it like this. Let's say N-type semiconductor, and I inject electrons into here. So injection of electrons and we examine the concentration of electrons from here to here. So this is distance, and we plot the concentration. We go in here for some particular device, some particular arrangement. We measure the concentration as a function of x. And what we observe is as follows. We see that the concentration goes like this. So this is n as a function of x. Okay? It's not a straight line going down. It has this behavior. All right, now what we would like to do is plot the current, the diffusion current resulting from this concentration gradient. The concentration is not constant. Here we have the highest because we're injecting the electrons right here. And the concentration keeps going down in a nonlinear fashion. So what we would like to do is plot the resulting diffusion current. Okay, no problem. It's just this, dN times dN over dx. So the diffusion current density J would be, because the derivative is negative, the current is negative. So the current goes like this. Here we have a higher slope. Here we have a lower slope. So the current goes like this. We have in magnitude, in absolute value, we have a large current at the beginning. So I can even start from here. And then the current decreases as we go farther into the material. Okay, so nothing exciting so far, but this poses an interesting question. We see that at this point we have a high current. So let's say at this point we have 1 milliamp per square centimeter. And this current is completely composed of free electrons. But then here, the current is less in absolute value. It might be 0.2 milliamps per square centimeter. And again, it's only consisting of electrons. So something strange is happening here. We had lots of electrons here carrying the current, but by the time we got here, we don't have that many electrons left. What happened to those electrons? When we injected these electrons into here, and they started propagating because of the concentration difference, they were rolling down this hill. Why is that they are disappearing as we go here? Why is that the amount of current is less? Are the electrons just disappearing in thin air, or is something happening to the electrons? Well, the answer is that if indeed we observe this behavior, it only means one thing. It means that the electrons that are propagating in positive x direction must be recombining with the holes that are present in that piece of semiconductor. So if we see this behavior, the only conclusion, the only possibility is that the electrons must be combining with holes as they go this way. And that's why we have fewer electrons over here than over here. So for this behavior, we observe that injected electrons recombine, we called it recombine, or you can just say combine, recombine with holes in the semiconductors. Okay? And that's why the current decreases as we go farther in. Now you may say, well, I doped this semiconductor with a donor, with let's say phosphorus, so much that the number of holes available is very, very small, orders of magnitude smaller. So that shouldn't exist. This shouldn't happen because we just don't have enough holes. We have very, very few holes for recombination. So if that is the case, then the plots will not look like this. So let's try the plots for the case that the number of holes available, the density of holes is so small that there's just not any significant recombination of the injected electrons with the holes. So for that, I will change the color of my pen to red, and this is what we observe. Okay, so if we work backwards, if we know that there is no recombination because we don't have that many holes in the semiconductor, then the current carried by electrons has to be constant. It cannot go like this. So the current has to be, for example, something like this. So this is the case of no recombination. Okay, now we work backwards. If J is constant like this, what should N look like? N should be a straight line with a negative slope. So N has to be like this. So that is the case of no recombination. So you see that diffusion still occurs. The gradient in concentration still exists, but it's a straight line. So if that's the case, then the current is constant. The current is carried primarily by the electrons. There are not that many holes in there, and everyone is happy. On the other hand, if the holes are not that small, then we will see something like this, and we'll see something like that. All right, very good. Let's move on, and let me just mention a few more concepts here. So we saw that the diffusion of carriers is characterized by this equation, and we have electron diffusivity and hole diffusivity in there. If you're curious about the values, let's see if I have those values somewhere here. Yes, so dN is 34 centimeter squared per volt. Oh, I'm sorry, centimeter squared per second. Centimeter squared per second. And dP is 12 centimeters squared per second. As you can see, I don't remember the units or the values of these constants because I don't use them very often, but that's okay. We can always look them up, and these are the values that we have. Okay, now let's go back to the concept of drift. Remember, for drift, this is what we had. We said the current carried by drift is given by the mobility times the electric field times the electron charge times the concentration of electrons, concentration of holes. So that is a drift current, that's the diffusion current. So in the drift current, we have a parameter called mobility to show how mobile the electrons are in the presence of an electric field. In diffusion, we have a parameter called diffusivity that shows how willing electrons or holes are to diffuse in the case of concentration gradients. So these are two different parameters, and they describe different types of behavior. But what's interesting is that there's actually a relationship between mobility and diffusivity, which we will use later on to simplify our equations. So that is called Einstein's relation. And Einstein's relation says that d over mu for a given type of carrier, electron or hole, is equal to kT over q. K is Boltzmann constant, T is absolute temperature, and Q is the electron charge. I usually remember K, 1.38 times 10 to the minus 23. And temperature, for example, 300. I don't remember the electron charge. But what I do remember is this whole quantity. This whole quantity actually has a voltage dimension. And this whole quantity is equal to 26 millivolts at room temperature. As you will see, this quantity K2 over Q appears in many, many types of studies that we do in electronics. So it's good to remember this voltage. It's good to remember its value. It's good to remember the expression. Sometimes this is called the thermal voltage. So sometimes we call this the thermal voltage. Okay, so Einstein's relation allows us to simplify things. In case we end up with a ratio of diffusivity and mobility, we replace it with K2 over Q, and we carry this on. As you will see shortly, this appears in some of our equations even today. Very well, let's see where we are. Okay. This concludes our study of charge transport or current transport in semiconductors. In summary, we have seen two effects: drift when we have a voltage, an electric field, and in response to that electric field, we obtain this type of current. And when we have diffusion, we obtain this type of current. And of course, we could have both of these at the same time in the semiconductor under some conditions. But it's good to remember that these are very different mechanisms and that they do different things, even though the final result is current conduction. And as we will see in electronic devices, sometimes we have that, sometimes we have this. Or in some part of the device, we have that, in some part of the device, we have this. So these are the two mechanisms that we have to remember. Very well, we are now ready to apply the knowledge that we have developed so far to the first electronic device that we can build, namely a PN junction. So for that, I will add a new page, and I will draw a line in the middle. Okay, so we're going to study PN junctions. The PN junction. All right. Well, as the name implies, there's a junction, meaning that two things are connected. And because we say PN junction, so maybe we took some P, we took some N, and we made a junction. We put them together. And that's what we call a PN junction. So, at a very high level, that's exactly what we're doing. We have a piece of P-type semiconductor. For example, silicon doped with boron, and a piece of N-type semiconductor. For example, silicon with phosphorus atoms, and we have attached them together to form a junction right here. This is a two-terminal device. This is one terminal, this is the other terminal. So it's good because we are used to two-terminal devices, resistors, capacitors, inductors. The only device that we have seen that had more than two terminals was the transformer. But beyond that, most of the terminals we have played with have only two terminals: voltage sources, current sources, switches. So this device has two terminals. And it consists of a P-type semiconductor attached to an N-type semiconductor. So we call it a PN junction. Okay, so what's the big deal? Why do we study this device? Well, first let me give you a few examples of where this device is used. So in all electronic devices where we have chargers, adapters, where you take the voltage from the line, from the wall, 110 volts or 220 volts, and then eventually you bring it and you convert it to 3 volts, 4 volts for a cell phone, or 12 volts or 18 volts for a laptop. In all of these devices, all of these chargers, all of these adapters, we need this type of device, a PN junction. A PN junction is one example of what we call a diode. So this device is also called a diode. And diodes are essential to building all of these various devices, chargers and adapters. So chargers and adapters. Anywhere that you use them, you have diodes in there. They have other interesting applications. For example, what we call voltage multipliers. Voltage multipliers. Voltage multipliers are circuits that increase the voltage. For example, there are some devices called photomultipliers used in medicine and other applications where we need a supply voltage of 1,200 volts. Okay? 1,200 volts is a very high voltage. So how do we create such a voltage? The line voltage that we have is 110 volts or 220 volts. So somehow this voltage has to be multiplied up to 1,200 volts. And that there, again, we use diodes and capacitors to do something like that. So they have many interesting applications in real life. Okay, now, this is the first semiconductor device that we study, and as such, it is the simplest because it has only 2 terminals. That's another reason we start with PN junctions or diodes. We don't jump into transistors because transistors are more complex. So first we have to learn how to walk before we learn how to run. And that's a good entry point for understanding semiconductor devices. Now, before studying the details here, let me just show you a quick experiment and see what happens. So, quick experiment. All right, so I will perform 2 experiments on this board to show you some interesting effects. First experiment, let's take a piece of N-type semiconductor and apply a variable voltage to it and measure the resulting current. What should we expect? Well, this is just a resistor. Remember, we calculated the resistance based on mobility and carrier density N. So it's just a resistor. So if I sweep Vx from minus infinity to plus infinity, I just have Ohm's law. So I know that Ix is equal to Vx over R. R is the resistance of this piece of semiconductor. And we just have a nice straight line, like so. And as you can see, the slope of Ix as a function of Vx is 1 over R. So this slope is 1 over R. So nothing dramatic, very simple. Okay, well, what if I try the same experiment with this beast, this PN junction? Now, we don't know what's going on in the PN junction yet, but I just want to give you a quick preview of what we will see. All right, so here's a PN junction. So, for example, we have P on the left, N on the right. And we perform the same experiment, a variable voltage source connected to the 2 ends, Vx, and we're trying to measure Ix. So, what do we measure? Let's see. So Vx Ix. Okay, well, if Vx is positive, we see some current. And the current does vary as a function of Vx. But it does not vary linearly. It varies like this. That's very strange, isn't it? Also interesting, if Vx is negative, what we see is that Ix is almost 0. So Ix is almost 0. So if you compare this with this, you see a dramatic difference between what a p-n junction does and what a resistor does. The p-n junction does not satisfy Ohm's law anymore. It has two types of differences with respect to a resistor. Number one, it has different behavior for positive voltages and negative voltages. It can't tell the difference. Positive voltages, we have current. Negative voltages, we have very little current. And the second difference is that when the voltage is positive, it's not a straight line like a simple resistor, but a strange function. In fact, it's an exponential function. So these two differences make diodes much more interesting and useful than resistors. And that's why they have so many applications, as I mentioned before. So our objective is to eventually derive these things, understand how they come about by delving into this device and seeing what's going on with the electrons and holes, etc. And of course, once we have this, somehow we would like to create an electrical model that we can use in analysis and design of circuits using such a device. So, but step by step, we'll take our time. All right, so let's, I would like to raise two questions that we need to answer to understand how a p-n junction operates. So let me write the two questions here. Question number one. When we have a p-type material, we have lots of holes, very few electrons. When we have an n-type material, we have lots of electrons, very few holes. So what happens when we attach them together? And right at this interface, what exactly happens? Do they fight each other? They don't dislike, they don't agree with each other. So what exactly happens, right? So we will ask this question formally. How do the charge carriers redistribute themselves after the p-n junction is formed? What happens to all these free electrons and holes? They are different here from here. So when we attach them right at this interface, what happens? So that's something we need to study very carefully. The second question is, after we understand that, how does the p-n junction behave under three conditions? Condition number one is what we call equilibrium. Equilibrium. Condition number two is what we call reverse bias. And number three, forward bias. These are all unfamiliar words and expressions. Don't worry, we'll get there. But these are two questions that we need to answer so that we understand how the p-n junction behaves and eventually reach this type of characteristic. Okay, so before answering the first question, I need to refresh your memory about a few things that we have studied so far. So let me change the color of my pen. Okay, so some observations. These observations are necessary before we can answer the first question. All right, so we buy a piece of N-type material, and we go in there just by itself without being connected to anything else in the world, and try to measure the concentration of electrons and the concentration of holes as a function of distance from here to here. So what do we see as a function of distance? Well, we know that we have lots of electrons and very few holes because this is an N-type material. So what we will see is that N is up here and P is down here. And that is the concentration axis. N is very high, P is very low. How much is N? Remember the equation we had. N was actually about equal to ND, the number of donor atoms per cubic centimeter, and P was Ni squared divided by ND. So far so good. Let's repeat this for a p-type device. So here's a p-type device. Here's our x-axis. So we bought a p-type device and we are plotting the concentrations. In a p-type device we have lots of holes, very few electrons. So we have lots of holes here. That's P. And we have very few electrons. So that's N. And we saw that the number of holes per cubic centimeter is given by the concentration of acceptor atoms, whereas the number of electrons is given by Ni squared over Na. I hope you can read this on the screen. Okay, so that's just a quick summary of what we have learned before for N-type and P-type doped types of semiconductors. Now, when we try to form a junction of a piece of N and a piece of P, like here, the notation can be very confusing. I have N here, I have N here, I have P here, I have P here. So I have to make sure that all of these parameters don't get confused. So we're going to add some subscripts to distinguish these from each other. So let me change the color of my pen so that I can emphasize these subscripts, maybe to black. So the concentration of electrons in the N-type material will be N sub N. Sub N refers to N-type material. Similarly, the concentration of holes in the N-type material will be P sub N. So P sub N. So the subscript refers to the type of material we have, P-type or N-type. Similarly, on the other side, if I have a P-type material, the concentration of holes in the P-type material will be denoted by P sub P. And the concentration of electrons by N sub P. So I hope that this is clear. You really need to be comfortable with this notation because we will use it extensively and then it can become a little confusing. Very well. So that is the situation when I bought a piece of N-type silicon and a piece of P-type silicon, and then I'm ready to attach them to form a p-n junction. Now, I should mention that if you do actually that, if somehow you go and buy a piece of p-type and a piece of n-type silicon and try to attach them, you will not have a p-n junction. Because for the p-n junction to behave as I mentioned before, this entire device has to be one single crystal. And we cannot create a crystal if by just attaching or gluing or melting two pieces of p and n together to form a junction. So in reality, we start with one piece of silicon here, and then we dope these differently to create p and n. We cannot just buy them and attach them. But assuming that we have a good crystal here and we have some p doping on this side, some n doping on this side, we are now ready to study it in detail. Okay, so let me consider the first case. Okay, so the next observation that I would like to make is the following. Let's consider a piece of n-type silicon just by itself. It has an abundance of electrons. It has very few holes. So the question I ask is, what is the net charge in this device? What is the net charge? Well, we said we have lots of electrons, very few holes. So does it mean that the net charge in this piece of silicon is negative? No, it does not mean that. Remember that this n-type material just consists of silicon atoms and phosphorus atoms, and nothing else. We didn't do anything else. So we still have charge neutrality because every electron that is present here has one counterpart proton in the nucleus of an atom. So if the electron is available from a phosphorus atom, that phosphorus atom still has a proton inside the nucleus. If the electron came from a silicon atom, that silicon atom still has a proton in its nucleus. So the total charge in this piece of silicon is 0, regardless of the doping level that we have, whether it's doped or not doped, or p-type or n-type. So we say we have charge neutrality. Okay, so net charge is 0. All right, now let's go one step farther and ask in the next question, what if I take that piece of n-type material and I happen to take one free electron out of here, completely out of the material? Then what happens? Well, that electron came from somewhere, let's say from a phosphorus atom, right? Now, because we took the electron out of the material, we have a positive ion left behind. So we will denote that by a circle with a positive in it. So if an electron is taken out or extracted of the device, then we have a net positive charge, and that's a result of a positive ion. A positive ion is formed. Okay, so like everything else, so if you take some charge out of some object, some device, yes, then there's the opposite charge left. So if you take an electron out of this, we have a positive charge left, and that positive charge is associated with one ion. So it's important to understand the difference between these two, because when we go to the equilibrium condition, we need to remember these. Very well. Now, with these, I think we are ready to embark upon our first study of the PN junction. So let me add one more page. All right. Okay, so what we will study now is the PN junction in equilibrium. And PN junction in equilibrium simply means after you form the PN junction from a single crystal, just leave the terminals open. Don't connect them to anything else in the world. So here's our PN junction. We have the terminals here on the two sides, but they are left open. They're not connected to anything else. Okay, this little line here indicates where the doping level changed from P to N, and we are assuming is an abrupt change. So it's P, and then suddenly it changes to N. And now, just to make sure that I have these right, so at this point I will call the left section N and the right section P. So N-type material and P-type material, and this is the junction interface. Okay, so now what happens? Well, let's remember from the previous page. So if I take it to the previous page for a second, remember what happened in N and P before we formed the junction. We had N sub N electrons per cubic centimeter on the N side, P sub P holes per cubic centimeter on the P side. These are the majority carriers. And then we have the minority carriers on this side, P sub N and N sub P. So we're going to form an interface between the P and the N and see what happens. So let's go back here and see what we get. Okay, so I need to draw those concentrations again so that we remember where we are. So we have a high concentration of electrons, N sub N. Okay, let me do this more carefully. N sub N. And a low concentration of holes, P sub P, P sub N. Then we have a high concentration of holes on this side, which we call P sub P. And then we have a low concentration of electrons, which we call P sub N. Right? That's what we have in the N-type and P-type pieces. Now, when they come together, something interesting happens. If you look here, we have lots of holes. We have a high concentration of holes on the right. We have a low concentration of holes on the left. So what should happen? We should have diffusion, because that's how conditions for diffusion are provided. We have a high concentration of some particular particle and some low concentration of the same particle. So the particles prefer to go to the low concentration area. So holes, which are majority carriers on the right, begin to roll down the gradient and go to the left. Similarly, electrons, which are majority carriers in the N-type material, begin to roll down this gradient and go to the right. So one hole starts from here and goes here. One electron starts from here and goes here. Now, remember the charge neutrality principle. Before we put these together, the N-type material was neutral. It had as many electrons, as many negative charge, as much as positive charge. This negative charge is counteracted by some holes and then some protons. Similarly, this guy was neutral. But now when I place these together, when I form this junction, an electron starts from here, which has a high concentration, and goes here, we have taken one electron out of this material. If I take one electron out of a piece of material, what happens? A positive ion is left behind. So for every electron that departs this section and goes to this section, we end up with a positive ion. A positive ion is an atom that has lost one electron. So here is a positive ion. So this continues. So we form lots of positive ions on the left side because lots of electrons are leaving the left side to go to the right side. What happens to the right side? Well, lots of holes are going from the right side to the left side. Every time a hole leaves, in fact, it is filled by an electron, so we form negative ions. So we have lots of negative ions here. So this continues. This continues for a while. We have a current consisting of electrons going from here to here. We have a current consisting of holes going from here to here. So if holes go from here to here, the conventional current also goes from right to left. Okay, so we have a current going this way. If electrons go from left to right, negative current is going from left to right, so positive current is still going from right to left. So for both of these components, we have a current going from right to left. So we have a current going this way. Holes going this way, electrons going this way. But that's strange, isn't it? How could we have a current if the terminals are left open? That goes against what we intuitively understand. Well, what should happen is that this current may flow for a while, but then eventually has to stop. And the question is, what exactly stops the flow of current? Well, we have these ions that are formed here. We have positive charge here, negative charge here. So in this area here, we truly have a charged object. Charge neutrality does not hold because we have positive ions or negative ions. So right around here, we have positive charge. And right around here, we have negative charge. If we have charge, net charge, we can associate an electric field with that net charge. So as we expose these positive ions on the left and negative ions on the right, we create an electric field in this region. Which way is the field pointing? Well, we just take a positive test charge and put it here and see which way it goes. So you put it here, the positive charge is pulled this way by these negative guys, or pushed this way by these positive guys. So the electric field is pointing from left to right. Okay? All right, so that's a lot of information coming through. We saw that we had a diffusion of these currents, the diffusion of these holes and electrons, which resulted in a current. At the same time, as these carriers were moving, they were leaving behind ions, and these ions formed a charge, a space charge, and that space charge starts creating electric field. So we have an electric field going from left to right. Okay, all right, so we have an electric field. Now, what does this electric field do? Well, the electric field says, if you place a positive charge here, I want to push it that way. So it doesn't want any positive charge to go this way. So if a hole wants to go this way, this field opposes it. Similarly, because of these negative ions here, the field says, if you bring a negative charge here, I want to push it that way. So if these free electrons want to diffuse this way, the electric field wants to stop them. So the electric field that is being created in this region is opposing the diffusion current of the electrons and the holes. So you can see now what happens, right? We have a diffusion of holes and electrons flowing. We have a current flowing. But as they flow, they leave behind ions. The ions create an electric field. The electric field opposes that diffusion current, and as a result, these currents begin to stop. So at some point, this field is strong enough to stop the diffusion of holes this way and the diffusion of electrons this way. And that's when the junction reaches equilibrium. Equilibrium means that the electric field has reached a point to stop the diffusion currents. Okay, now we call this region here, where we have only ions, all the free charge has left, has gone to the other side, we have only ions. This is called the depletion region. Depletion region. It means it's depleted of free charge carriers. We don't have any free charge carriers left here because we have only positive ions. Ions are not able to move around, so we don't have any charge, we don't have any current conduction. All right, that's what we call the depletion region, and we see that we have an electric field. Okay, so our time is up, and we will talk a little more about the equilibrium condition in the next lecture, and then we go on to answer the other two questions, the other question, namely the other two conditions, namely what happens when we have reverse bias, what happens when we have forward bias. And those terms, although unfamiliar, simply mean what do we see here and what do we see here? Positive voltages and negative voltages across this p-n junction. I will see you next time.